Hello, in this video we are going to go over the solution of the problem 210, course schedule second. Okay, let's start with an example. And in this example we have 7 courses. We have number of courses here as 7. So we have 7 nodes, and these nodes are connected to each other using this array prerequisites. For example, for the first element, 5-4 means that course 4 is the prerequisite of course 5. And we can draw the other connections and we will end up having this graph here. And if we look at this graph, we can see there is a cycle in this graph. And because we have a cycle here, it is not possible to take the courses. Because if we try to take the course 2 here, first we need to take the course 6. But before taking course 6, we need to take the course 0. Before taking the course 0, we need to take course 3. Before taking the course 3, you need to take course 2. So there's a cycle here. So it is not possible to have a correct order of taking courses here. So there is a cycle and we are going to return an empty list as the result. Now let's look at this example where we changed one edge, and now with this new direction of the connection, we don't have a cycle and we actually have a directed cyclic graph, and so because of that it is possible to take these courses. Okay, let's start writing the code. Okay, for solving this problem we are going to go over each node, and when I'm at a node I'm gonna conduct DFS. So I'm gonna visit all of the nodes one by one. For doing that we are gonna have a for loop, and we say for course in range of number of courses, we are going to conduct DFS. We just put a comment here as a placeholder, and now we are gonna create our DFS function, and we say define DFS as cyclic. So what I'm gonna do is that we are gonna have an input to this function as the course that right now we are visiting. What I'm gonna do is this. When I'm visiting one course, I'm gonna go and visit all of the neighboring nodes of that course because we are conducting DFS. For doing that, it's much more convenient if I have a nice dictionary format that we could have a list as the values and nodes as the keys. So for doing that, let's use our prerequisite array and create that dictionary. So let's initialize that. This is gonna give me a dictionary, and now I'm gonna fill out this dictionary. I say for the course and prerequisite in prerequisites, the array that we have, I'm gonna say dictionary with the key prerequisite dot append C, the course. Let me print this dictionary here that you can see what we are doing. And I'm just gonna put pass here. Okay, let's run this. So the keys are the nodes. You can see we can 0, 1, 2, 3, 4, 5, 6. And for each node, we can see the neighborings. So for example, for the node 6, I have 2 neighbors, 2 and 0. Let's go back and see node 6. So for node 6 here, I can visit node 2 or I can visit node 0. Okay, there are 2 neighbors of node 6. Okay, now I have this dictionary and I should be able to loop over that list for each node. So we come back to inside our function DFS, and we could say for neighbor in D of course, because that is a course that right now node that we are visiting. So for that one, what we are gonna do this. So we are gonna say if DFS cyclic of neighbor is false, we return false. So we are saying that if for any of the neighboring nodes, we find out that it's not a cyclic, there is a cycle. So in that case, we are just gonna return false. Okay? And if it is not the case, at the end, I just return true. Okay? Okay, to recognize that if we are visiting a node 2 times and we have a cycle, we need to create a set here. So what I'm gonna do is to create an empty set here. I'm gonna call this set as cycle scene. And this cycle scene is gonna be an empty set at the beginning and out of the DFS. Okay? Now, whenever I'm at a course, I add that to my cycle scene. I say cycle scene dot add course. Now I'm at that cycle scene. Okay? Now that is added. Okay? So we go forward. But whenever because it is a recursion, whenever I come back, I make sure that is not already inside that scene and say if course in cycle scene I return false. Okay, so in this way I'm recognizing a cycle, because if it is already visited, now that exists in the cycle scene, and when I'm visiting a neighbor, I say, okay, that is inside the cycle scene, so that is already visited, we have a cycle, so return false. Okay, that returns false, it's gonna be return false, and then we return false at the end for that node. Okay, the most important part is this. So after we are done with this cycle scene, so now we have to empty that for the next course. So I'm gonna say cycle scene dot remove this course. Let's see on a graph why we are doing this. Okay, let's say at the beginning I'm visiting the node 0 and I'm adding that to my cycle scene. And imagine that I'm not removing that from cycle scene by mistake and keeping the 0 inside that. Let's see what happens. When I'm coming for another node, for example, I come for node 3. So now my course is 3. So I'm going to conduct DFS and I come to its neighboring node 0. But it's going to say, oh, that is already visited. And it thinks that we have a cycle, while there is no cycle here. So whenever I visit a node and I'm done with that node, at the end I have to empty its cycle scene. Okay? Okay, now we are done with that node. I'm gonna record this node. So for recording that, let me define an empty list at the beginning. So I'm gonna say result equals empty list here, and here I can append to that. Result.append and course. Okay, so now we are adding that to our result whenever it's done. So whenever it is finished, there is no neighbor, we are done with that node, we add that to our result. Okay, so far we saw that we have a for loop that we are going to go over all of the courses one by one, and for each one we are going to do DFS that we just showed here. Okay, if we do that, we are going to end up having n to the power of 2, because for each node, we are going to do one independent DFS. But we don't have to do that. If we already did DFS for one node, we don't have to do it again. So for saving time, what we are going to do is this. We are going to create another set. So call this scene here. And at the beginning, that is an empty set. And then I'm gonna do this. I'm gonna say if course in scene return true. So it says I'm at this course and I'm gonna say and I can check to see if DFS is done for that course, just return true. Don't do anything else. So in that way we are saving a lot of time, and the time complexity is gonna get into the order of n. Okay? And we have that one. Let's see what else we need to add. So, okay. The last thing that we need to care is that if this function returns false here, so if that is happening, so I'm gonna return an empty list. So what I'm gonna do here is says, if for these courses that we visit, to say if DFS cyclic of course equals false, it means that at some point in the graph there's a cycle. In that case, I'm just gonna return an empty list. Otherwise, we just return our result. That's the list that we created here and appended the stuff to that. Okay. Let me organize this better. And we also should make sure that for this scene set that we are gonna check, we should make sure when we are done with a node, we should add that to that scene. So here, when I'm done with a node, I just come here and say scene.add that CRS. Okay. Okay, now we run it and we can see the result. And the last point is that when we save the courses in our result, that was the time that we are done with one node. So as we are saving these things to our results based on the finished nodes, at the end, we are gonna have a reverse direction from what the problem is asking from us. So let's look at that. If you look at the result here, we can see this is actually reverse to what the problem is asking us, because now we save the nodes based on whatever it is finished. So for example, 0 got finished first. We added that to our result. Then we finished 1, then we finished 3, and so on. But the order of the courses that we are going to get is actually from the beginning to end. So the only thing that we need to do is to reverse this list and return the result. Okay, now we just need to reverse the result and show the final list, and that's gonna be this one. And this is what we expect to see. Okay, now let's talk about time and space complexities. For the time complexity, we have a for loop here that we are gonna go over all of the courses, and then for each course inside the DFS, we are gonna go and visit all of the neighboring nodes. So the time complexity is gonna be the order of number of vertices plus the number of edges in our graph. Our space complexity is also number of vertices plus edges, because we are using this recursion solution, and also because we have created this dictionary that the keys are the nodes, and also we have the values, that the values are the neighborings that are connected to that nodes, that are number of edges. Okay, as the result, the overall space complexity is also vertices plus edges. The most important point about this problem was to create two separate scene sets, and one of them, which is a cycle scene, is the one that needs to be emptied when we are done visiting a node, and the other one, the other set, used to make sure that we are not duplicating a calculation and to save time for us. Okay, thank you so much again for watching this video.